So now let's talk about more appropriate error metrics. So which is basically the third problem, which is changing the evaluation metric. Now out of all the things that are mentioned here, we have already talked about confusion matrix, we have talked about precision, recall, sensitivity, specificity, AUC, ROC, F1 score, and Cohen's Kappa. Cohen's Kappa is something that we have not talked about. I'm gonna be talking about it right now, but apart from that, you already know what is all of this, right? So kind of give you a recap for all of it. This is a confusion matrix, right? Confusion matrix looks like this: actual, pred, positive, negative, positive, negative. So this is TP, this is FP, this is FN, and this is TN, right? So we know accuracy. Accuracy is nothing but TP plus TN by the entire thing. So accuracy is nothing but TP plus TN by the entire thing. Next is recall. Recall is nothing but basically out of the given positive examples, how many did you actually pick up correctly, right? So this was your total number of positive examples. Out of this, these are the ones you could pick up. So TP by TP plus FN. And precision is nothing but out of the predicted, the ones that you predicted, right? So these are the ones you predicted as positives. How many did you actually pick up, right? So this is TP by TP plus FP, right? So this is what precision and recall is. I'm not sure if you can follow my handwriting there. I'll try and make it, yeah. And now what was AUC? AUC was nothing but a plot of TPR, which is nothing but recall. So this is what is TPR. FPR is nothing but 1 minus specificity. By the way, recall is the same thing as sensitivity also. This is sensitivity. And so FPR is 1 minus specificity. Specificity is nothing but the same thing as recall, but for negative class, right? So for negative class, that is basically out of the given negatives, how many did you pick up? So TN by FP. So this is specificity. And 1 minus specificity is what we have as FPR. So AUC curve is nothing but a plot between TPR and FPR. And how you get that plot is basically you have your prediction probabilities and you change your threshold, right? If you remember the threshold, right? Threshold concept was basically anything you say that what is your final class prediction is based on your threshold, right? If your probability is above that threshold, it's class 1. If it's less than that, it's class 0, right? So for a binary classification problem, we would basically take multiple thresholds, and based on that, you would come up with a curve like this. This is the ROC curve. And the area under this is your AUC. So this is the whole concept that we have already talked about. So now that you kind of recap that, let's try and go ahead and understand what is Cohen's Kappa, right? So what is Cohen's Kappa? Cohen's Kappa is something that is basically a measurement of how well is your model performing. So what is the observed accuracy, which basically as compared to the expected accuracy, right? So we know that observed accuracy as such is not a good measure of evaluating your model, right? Especially more so if you have a class imbalance problem. So we don't want to use observed accuracy as it is, but we want to kind of see how that observed accuracy compares as expected to expected accuracy. Now expected accuracy is a concept that you are not familiar with, so now I'll kind of introduce that. So that is something that we are going to talk about. So Kappa statistics is a metric that compares the observed accuracy to the expected accuracy. Now observed accuracy is the same thing as the accuracy that we have been dealing with, TP plus TN by the entire thing, right? So that is what is observed accuracy. So expected accuracy, and we know that observed accuracy is not the best thing to go ahead with, at least in class imbalance. So what we are now going to do is take the observed accuracy, but instead of reporting it as it is, we are going to try and compare it against the expected accuracy based on class imbalance, right? And then see how our model performs, right? Don't get confused by looking at this kind of a confusion matrix. sorry, don't get confused by looking at this kind of a confusion matrix. B is basically nothing but the actual. Yes and no are basically positive and negative, and A is the predicted, right? So P observed is nothing but 2 positive plus 2 negative, which is basically this plus this by the entire thing, right? This is observed accuracy. Now what is the expected accuracy? Expected accuracy is the fact that if I randomly pick up one of the samples, what is the probability that it would be correct, right? So now there could be two things. You could randomly pick up a yes or a positive instance, or you could randomly pick up a negative instance, right? So expected accuracy is nothing but what is the probability that if you pick up a randomly positive instance, you have classified it as positive, or if you have randomly picked up a negative instance, what is the probability that it is classified as negative, right? That's an easy concept, right? So again, repeating it, the concept of Cohen's Kappa is basically trying to measure expected accuracy, and expected accuracy is nothing but the fact that what is the probability that if you randomly pick up some example from the data set, it would be classified correctly. Let's kind of walk you through the calculation so that you don't get flustered around this, but yeah, kind of hold on to your thoughts. So out of this, so if you remember the confusion matrix A, B, C, D, so out of this, if you look at it, and the probability of so now let's go through the examples and understand this. So out of the given confusion matrix, you can clearly see that A plus B observations are yes and C plus D observations are no, right? Hence the probability of a randomly chosen observations being classified as yes is A plus B by A plus B plus C. And similarly, probability of a randomly chosen observation being classified as no is C plus D by A plus B plus C plus D, right? And now what is the probability that you would, given any instance, it would be classified as yes, right? So what we saw was what is the probability that it's given any observation, what is the probability that it's a positive or a negative class. This is what we are talking about, right? Probability of a randomly chosen observation being belonging to positive or negative class. Those are the two probabilities. Now what is the probability that given an observation it would be classified as yes? This is given by A plus C by A plus B plus C D for positive. If it's randomly classified as positive, the probability, and the probability for being randomly classified as negative is B plus D by A plus B plus C plus D, right? So clearly, as I already explained, there are two basically cases that can happen here. You randomly picked up a positive instance, the probability of that is P1, and it is also being classified as yes, that is P3. Those are the one instance when you would get a correct answer, and the other scenario where you get a correct answer is basically the case where you have selected a negative example, the probability is P2, and it's also classified as a negative example, the probability is P4, right? So hence the expected probability of a randomly chosen classifier is P1 into P3 plus P2 into P4, right? So P1 into P3 is basically what is the probability I've randomly chosen the positive instance into what is the probability that I've given any observation, what is the probability that it is classified as a positive instance. Similarly, P3 is the probability that I've randomly chosen a negative instance. P4 is the probability that it is classified as a negative instance. So now you combine that, as I've said, P expected is nothing but PS plus P no, and PS I have already explained to you is basically P1 into P3, and P no is P2 into P4. So now you know kappa is now nothing but basically a comparison of P observed and P expected, right? So this is kappa. Kappa is nothing but P observed minus P expected by one minus P. As you can clearly see, the maximum value of kappa equals to 1 if P O equals to 1, right? Which is basically to say the observed accuracy is 1. Now observed accuracy is 1 means 100% accuracy. Remember, this P observed is the original accuracy, right? PE is basically what we calculated using PS plus P no. PE is basically that, PO is the original accuracy, and you can clearly see the original accuracy. If it is 1, the kappa value kind of goes to 1, right? And minimum value is kappa equals to 0 if PO equals to PE, right? I'm not sure if you're following that. handwriting, yeah. PO equals to P, which basically means your model is basically as good as an expected model, right? Expected accuracy. Model is basically not learning anything. Given a random chance of it being classified, yes, the probability that you get is the same that you have from your model, and that's why your model is not performing good. So higher the value of kappa, the better the model, right? So that's something we already understand. If your model is performing as would have been random expectations, that's when you would give a kappa value of 0, right? Cool. So now that we understand what it is, obviously this is something to kind of reinforce this. Cohen's Kappa is again not something that you would use a lot in industry. Cohen's Kappa is basically used for those kind of scenarios where you're say trying to measure agreement between two observations, right? For the same kind of data points, you're trying to see what is the observation between inter-observer agreement on those kind of things that you would want to use Cohen's Kappa. But frankly, for the rest of all the class imbalance problem, you would tend to use mostly AUC kind of a matrix, specifically because precision and recall are still dependent on thresholds, right? Precision and recall basically are under the assumption that you have recognized something as a positive and negative class, and we don't know the thresholds for identifying we don't know the right threshold for doing that, and hence using 0.5 as a basic threshold to do precision and recall is not the best idea. Hence we want to stick with something that is threshold independent, and that's where AUC comes into picture. So for most of our class imbalance problems, you would tend to go ahead with using AUC as a default evaluation metric, right? So this is something I have already talked about Cohen's Kappa and how when the performance kind of goes. So higher the value of Cohen's Kappa, higher the better the model, right? So now we have examples of two classifiers with given confusion metrics. Let's have a look at the kappa. So now you can calculate this at your end. Take time, pause the video if you want to calculate the thing, Cohen's Kappa value. You would see the Cohen's Kappa value comes out to be 0.878. This is some other value, so you can clearly see the accuracy numbers have not changed much, right? So in this case, the kappa value is 0.49, which is drastically lower. So this is a classifier B, which you don't want to go ahead with, even though if you compare the accuracy number of classifier A and classifier B, they would come out to be exactly equal, or not exactly equal, they would come out to be somewhat roughly equal. Very similar values, right? The point here being that if you're trying to use accuracy as a blanket metric for all your problems, you're going to land up in trouble. So please don't do that. For class imbalance problem, specifically not, right? If you see class imbalance, definitely stay away from using accuracy. Try and go with precision recall. I would still say don't try and do that. I've already explained why. Try and stick with AUC, or if you want to go for something exotic, go with Cohen's Kappa. But just remember that in Cohen's Kappa also, it's not completely independent of threshold. So there's gonna be still some problem with that.
Log on to GreyAtom's learning platform to unlock more free content. Subscribe to our channel and hit the bell icon for regular updates.